Hey super scientists, we are going to tackle the chemistry EOG review today. I am going to go over what we talked about with periodic table as well as intro to chem. And this is Miss Kerr. Just try to follow along, try to write as fast as you can, and recall back to the very beginning of the year what we talked about with chemistry. So the first part says synthetic, and what you want to think of is anything that is man-made. When we look at the periodic table, we're going to look at the row that is called the lanthanides, and that is all the way at the bottom of the periodic table. Those two rows that are separate at the bottom are called the lanthanides. Something that we have in our everyday world that's man-made, synthetic, would be plastic. So that is a common man-made material. Natural is going to be mean made in nature. And where you find most of those, with a few exceptions, is in the main part of the periodic table. So I'm just going to put main PT. Okay, so things like gold and silver, anything we've really talked about with the alkali metals, transition metals, metalloids, nonmetals, those are occurring naturally in nature. So those main ones we've talked about all year. All right, now we're going to skip down here and talk about subatomic particles. That's what this says where your little hole is. Protons, the charge is going to be positive. The location is in the nucleus of the atom. Neutrons are neutral. Those are also located in the nucleus of the atom. When we talk about atomic mass, it's going to be the protons plus the neutrons in the nucleus. Electrons are negative, and they are in the electron cloud which surrounds the nucleus. So how do we use the periodic table? So it says use the element carbon for this example. So on the periodic table, and we've got the square that would be on the periodic table right over here. So the atomic number is located at the top, and that's going to be 6. Okay, that number tells us the number of protons, which is also 6, and it tells us how many electrons, which is 6. Okay, so all three of these numbers are the same. Now the atomic mass is going to be this decimal number at the bottom of the square, 12.011. All right, now mass number is this number rounded, and you're just going to use regular math rounding. So after the decimal, if it's 0.5 and higher, you're going to round up. If it's less than 0.5, like it is now here, 12.011, we're just going to keep the whole number the same, so just 12. All right, now, so to get the number of neutrons, we want to take, we know neutrons are in the nucleus. We don't know what this number is. So we're going to take the total mass, so the mass number, and subtract the protons to get the neutrons. So if this plus this equals the mass number, we're going to take the mass number minus protons to get the neutrons. Okay, so in this case, we're going to take the mass number of 12 minus protons to get 6, which is 6, and we get 6. So in this case, protons, electrons, and neutrons all equal the same thing. That doesn't always happen. All right, let's skip to this box on the right. And we had practiced drawing some Bohr models. So we're going to do carbon for this as well. Now this first circle is your nucleus. So inside your nucleus you have 6 protons. I'm just calling that 6p. And you have 6 neutrons, 6n. All right, now we have the orbital shells that go around the nucleus, and those hold the electrons. So in this first orbital shell, we are allowed 2 electrons. Well, for carbon, we need 6 electrons, okay? And so we do need those 2 electrons, right? In the second orbital shell, we are allowed 8 electrons. Do we need 8 electrons? We need a total of 6. So we don't need 8 in this next ring, but we're allowed to have them. So all we need is to get to 6. So we already have 2, so we just need 4. And usually we put those in pairs in these next rings. So 2 here, and I'll just put 2 on the other side over here. So when you count the dots or the electrons, you should have 6 total. So 1, 2, 3, 4, 5, 6. So we're all set. All right. How is the periodic table organized? It's organized by increasing atomic number. So from left to right, and I'm just going to abbreviate some things, so the number sign. So from left to right, we have what are called periods. Those are the rows that go horizontal left to right. If you look in those, this top number is going to show increasing from left to right as you go through the table. All right, we also have it organized by groups and families. Those are the vertical columns. Those are really important because they show how elements have similar properties. So if the question asks you which element has similar properties to carbon, and it gives you 4 answer choices, you're going to find carbon on the periodic table. You're going to look in that vertical column, which is group 14 for carbon, and you're going to find which answer choice is also in that column and has similar properties. All right, we also need to know our big groups on the periodic table: metals, transition metals, metalloids, nonmetals. All right, so metals, what some characteristics you need to know of those, or properties as we have written here. They are shiny. They are easily shaped or molded. They are good conductors of heat and electricity. Excuse me. All right, they are in groups 1 through 12, except for hydrogen. Hydrogen is not a metal. They are in mixed groups, groups 13 through 16, so columns. All right, so mixed group means there's other things in those groups: metalloids, nonmetals. This is the largest group on the periodic table, right? This is left of the staircase. All right, some examples are sodium, Na, lithium, and one I always like to put is aluminum, because aluminum is that one that is on the staircase, okay? It's underneath boron, it's on the staircase, but it's the only one on the staircase that is not a metalloid. It is a metal, and we know that from aluminum foil. All right, conductivity means the ability to conduct heat or electricity. I'm sorry, I skipped down too far here. Sorry. Transition metals, we're going to add to this, okay? They have a high melting point. They have a high boiling point. And I'm just going to put PT for point. And they are very hard and durable. And that's why they're used for pots and pans and things like that. All right, this is the middle of the table. So when you look at the table, they're right in the middle. They are groups 3 through 12. Things like gold, silver, tungsten, which is W, copper. So some very common ones we hear of all the time. All right, metalloids. Metalloids share properties of metals and nonmetals. So we call them semiconductors. All right, they are located on the staircase, stair step. It's called a couple different things, but over toward the right, they are on the staircase. The only one on the staircase that's not a metalloid, again, is aluminum. All right, so these are, the staircase is in groups 13 through 17. Not all of those are metalloids. Things like boron, silicon, arsenic, okay? Nonmetals are mostly gases. They are poor conductors of heat and electricity. They typically are brittle if they are in solid form. All right, and these are found to the right of the staircase. All right, neon is a noble gas. So again, noble gases do not like to react with other elements. Fluorine is a common one. Chlorine is a common one. Those are both halogens. Halogen means salt forming, and anything in the halogen family is very reactive. Okay, so those are the most reactive nonmetals again. All right, so we're going to transition kind of to your intro to chem, where we talked about physical properties, chemical properties. So if we just look at kind of a definition here, physical properties involves things that can be measured without changing the physical composition. So we're not changing what the object or the material is. So when we talk about a physical property, one is conductivity, ability to conduct heat or electricity, things like electronics. The lab we did at the very beginning of the year was connecting a circuit. So we connected a circle to light up a light bulb. That shows conductivity. All right, ductility means that it can be pulled or stretched into a wire. This is a property of metals, that it can be pulled or stretched into wire. Think of electrical wiring. Electrical wiring in your house. So behind your outlets, you would see electrical wiring. We also see electrical wiring outside on the telephone poles. All right, magnetism, force of attraction. So I think we all know what a magnet is, okay? It generates electricity, computers. We talked about really tiny magnets being parts of earbuds and things like that. So, you know, as we get more advanced, things start to get kind of smaller. Solubility is a substance that dissolves in water. Sorry, a substance that dissolves in another substance. Okay, remember, water is the universal solvent. It dissolves a lot of things. A solute is Kool-Aid. Kool-Aid dissolves in water very easily. Sugar, salt, we talked about being solutes. All right, and then malleability, again, a characteristic of metals. It can be hammered into shapes. I always think of aluminum foil, aluminum cans that hold soda. They can be hammered into shapes. Some other things, jewelry. Okay. So sometimes it helps to think of an example of something that you know in your everyday life, and that makes it a whole lot easier to think through some of these problems. All right, the next box is chemical properties. Chemical properties relate to how a substance changes its chemical identity. So we are getting a whole new substance when substances go through a chemical reaction. All right, so our first one in the box here is chemical reactivity. How likely an element is to combine with another element. So for instance, the alkali metals in group 1, if we mix them with water, we get an explosion, we get boom, okay? So we get a violent chemical reaction. Acidity. Acidity is the measure of how acidic or basic usually a solution is, okay? And so we really talked a lot about pH of water, drinking water. We want it to be a 7. We want it to be neutral. Flammability is the ability to catch on fire or ignite. Okay, so for this one, we're talking about group 2. All right, some of those group 2 metals we see in fireworks. All right, they're very flammable, like magnesium. And so they are used in fireworks a lot. Oxidation is formation of rust. We talked a lot about that at the beginning of the year. So typically you have a metal present, you have oxygen present. That's where, you know, the word oxidation comes from, oxygen. And usually there's moisture. So if you leave your bike out and it rains and you leave it out, you know, a long time, it's going to mix with the oxygen in the air and it's going to cause that metal to rust on the bike. All right, chemical changes. Chemical changes are really important, or chemical and physical changes are really important to our introduction to chemistry unit. We talked a lot about these. All right, so this, you got to write kind of a lot on this line, so try to write small. A physical change is a change you can see without a change in the substance. So a change you can see without a change in substance. And an example of that is any physical or state change. So for instance, ice melting to water is a state change. And so you can see the change, but it's not changing from water. All right, lots of other examples. Painting a block. You're painting it, you're changing the color, but you're not changing what it is. It's still a wood block. Hammering aluminum into foil. You're just changing the shape of the aluminum. You're not changing what it is. It's still aluminum. All right, chemical change is different. So you're changing the chemical makeup of the substance. Change in the chemical makeup of the substance. All right, so a new substance is formed. So what we just talked about previously, rust is a new substance that forms on a bike that you leave outside. So we did a bunch of experiments, and what you were to see were some indicators of a chemical change. So what was happening that said, yes, this is a sign that a chemical change is changing some of these substances. So one of the first ones here is precipitate. Now this does not mean precipitation, rain, snow, sleet, hail. A precipitate is a solid that forms from two liquids. So when you mix, for instance, two clear liquids together and it changes to bright yellow, that's not painting. That's something that happens different. And if it's changing color, okay, so it's changing bright yellow, but it's also forming a solid at the same time. And so there's an indication that, you know, it is a solid which doesn't normally come from two liquids, and so it's a chemical change, and we have a drastic color change. All right, gas production, we saw this in a couple of different experiments that we did. It gives off bubbles usually. So if you see bubbles, it tends to be gas production. Now we're not talking about boiling, because boiling is just water going from a liquid to a gas. That's still water. All right, if something gives off light, like our circuit experiment where we lit up the light bulb, that's going to be an indicator of a chemical change. If any new substance is produced, so we see a brand new substance produced, that's going to be an indicator of a chemical change. Then we did our baggie lab, and that was cool. That showed one of them was an exothermic reaction, so energy was given off, and the baggie got hot. Exo means out, right? So use your stems there. Endothermic, one of our baggies, the energy was absorbed, and so the baggie got cool. It got cold, cool or cold. So that was one of the baggies got warm, one of the baggies got cold or cool, and so those were examples of endo and exothermic reactions. All right, the next part, for elements, compounds, mixtures, this year we've really tried to look at some pictures during warm-up and things to try to distinguish between these. So you have the pictures, and we'll try to match those up with these definitions here. All right, so in this first blank is elements are pure substances that cannot be changed into simpler substances. Compounds are pure substances that are composed of two or more different types of atoms that are chemically combined. Compounds can only be changed into simpler substances called elements through chemical reactions. So, for instance, we can take water and it can go through electrolysis to break it into hydrogen and oxygen separate atoms, but we have to create a chemical reaction. All right, so going over the pictures, elements are going to be in this top picture here, element 1, element 2, and then this is showing a compound, maybe water, because you see the Mickey Mouse, right? So you've got the ears are different size, shape, maybe color, if this was in color, than this atom here. So we can tell that they're different things connected to each other, even though it's in black and white. All right, and then you have mixtures. Mixtures are physical combinations of two or more different substances that retain their own chemical properties and are just combined physically. Mixtures can be separated by physical means. We talked about several of these. Filtering, filtration, sifting, evaporation. Mixtures may be heterogeneous. Using our stems, we can see and separate different parts, hetero. Okay? Homogeneous cannot separate the different parts. It is a mixture where we cannot see the different parts. This would be a picture of a mixture. So whether it be heterogeneous or homogeneous, this is still going to be the mixture because it's showing the different parts mixed together. All right, and then our last part, we talked about balancing equations. And when you think of balancing equations, you should think of the law of conservation of matter. All right, it states that matter cannot be created or destroyed. So things cannot just appear out of nowhere or be disappear out of nowhere. The mass of the reactants is equal to the mass of the products. All right. So it says to circle the products. Products are always at the right. It's what comes out of the reaction. All right, underline the reactants. Reactants are what go into the reaction. So what do we put together to form the reaction? Then it says put a box around the yield sign. So we're going to put a box around the yield sign. Based on what you know about the law of conservation of matter, how many grams of CH4, which is methane, are there? So we have to do a little bit of math. So our atoms on each side have to equal each other. All right. So when we count these atoms of each of these elements, those have to equal each other, which they do. We've got 1 carbon, 1 carbon. We've got 4 hydrogen. Here we've got 2 times 2 hydrogen, which is 4. So that's the same. And then we've got O2, right? Well, this is where we're thrown off a little bit. So we've got O2 over here, but we've got 2 O's over here. So we've actually got 4 oxygens. So to balance this equation, we can actually add just a 2 in front there. So now we've got 4 oxygen over here. We've got 2 oxygen here, 2 oxygen here, and that equals 4. So we are all set atoms-wise there. Now we've got to balance it by grams. So this side has to equal the same amount of grams. This side has to equal the same amount of grams. So how do we go about that? Well, you've got both of these. So let's add these up. 44 plus 36, and that's going to give us 80 total grams on the right-hand side. We need 80 over here. What math do? We do 80 minus 64, and so this arrow is going to be our answer, which is 16. All right, so our answer on the line over here, how much CH4 do we have? 16 grams. All right, thanks, super scientists.